Welcome. Let's look at dimension of physical quantity. The dimension of physical quantity is expressed in terms of mass, in terms of time, and in terms of length. So in dimensional analysis, we express physical quantity in terms of mass, in terms of time, and in terms of length. Let's look at physical quantity and their dimensional analysis. Here we have quantity, the derivation, how we come about, then the dimension. Let's look at area. Area is length times breadth. So dimensionally, we can write area as L squared. Also, volume is length times breadth times height. So dimensionally, that is volume. Density. What is density? Mass times volume. So dimensionally, mass is m, volume L to power 3. So this is the dimension for density. Let's look at other physical quantity. Speed. Speed is distance over time. Distance is L. Distance is the same as length. Then time. So this is the dimension for speed. Velocity is displacement over time taken. So is TLT to power 1. What of acceleration? What is the dimensional analysis for acceleration? Actually, acceleration is change in velocity over time. And velocity, we have gotten it to be this. So this is the dimension for acceleration. Let's look at another one. Force is mass times acceleration. So mass is m, acceleration is L_t to power 2. Is it difficult? No, it's not difficult. So let's look at other example, other physical quantity. Weight, this number 8. What is the dimension for weight? Weight is mass times acceleration due to gravity. Acceleration due to gravity. So dimensionally, mass L_t to power 2. So this is the dimension for weight. Let's look at other ones. Dimension for momentum. What is the formula for momentum? Because that is the starting point. Momentum is mass times velocity. Mass is m, velocity L_t to power 1. Is it difficult? Also, pressure. What is the formula for pressure? Pressure, force over area. So, force, what is the dimension for force? Is this m_L_t to power 2, and area is L squared. So this will give m L minus 1 T minus 2. So the last one here is work. Work. And work is what? Force times distance. What is the dimension for force? mL T to power 2, and distance is L. So the dimension for work is Lm squared T minus 2. So these are physical quantities, the derivation, the formula for them, and this is the dimension for each of the physical quantity. It's good you have idea about each of the physical quantity. You know how they are derived. The derivation is just the formula. If you remember the formula, the next thing, using the three quantity that we earlier mentioned, mass, length, and time, we can use it to express the dimension of any physical quantity. Okay, the next thing we want to look at is application of dimensional analysis. Where do we use dimensional analysis? Why are we even study dimensional analysis? Let's look at the application of dimensional analysis. The first application is that through dimension or dimensional analysis can help us in the verification of correctness of physical equation. You have an equation, is it correct, is it not correct? Through dimensional analysis, we can check the correctness of an equation. If not, anybody can write anything and call it an equation. Example, let's look at how we apply this. Example, V equal to U plus AT. I know you are familiar with this equation. This is one of the equations of motion. Is this equation correct? Let's look at it dimensionally. V dimensionally is what? Lt to power 1. This final velocity. Initial velocity still the same, to power 1. Acceleration, we have gotten it before. Acceleration Lt to power 2. Then time is t. Let's substitute it here and see. We substitute, we will have the left hand side, Lt to power 1 will be equal to Lt to power 1 plus our acceleration Lt to power 2 time t. So if we look at this, you know this is to power 1. So t to power 2, t to power 1, you have Lt minus 1, Lt minus 1. So this will give 2Lt to power 1. This 2 is a constant. So if you see, the left-hand side is equal to the right-hand side. So dimensionally, this equation is very correct. So this is one of the application of dimensional analysis. Remember, we are looking at dimension of physical quantity. Okay, let's look at other application of dimensional analysis. The second application is that it helps in derivation. It helps in derivation of units of physical quantity. It helps in derivation of units of physical quantity. Let's look at example. Momentum. is mass times velocity. Assuming a student don't remember the unit of momentum and he has idea about dimensional analysis. With this formula, mass is written as m dimensionally and velocity is Lt to power 1. The next thing is, what is the unit for mass? Is kilogram. The unit for length is meter. Unit for time is second. So with this, we have gotten the unit of momentum. So this is another application of dimensional analysis. It helps us to derive unit of physical quantity. Any physical quantity at all that you don't remember the unit, with the help of dimensional analysis, one can easily get the unit. Then the third one, looking at application, the third application of dimensional analysis of physical quantity is that it helps in derivation of exact form of a relationship, between physical quantity, between physical quantities when the mathematics is too difficult. Do you hear that? Through dimensional analysis, we can derive the exact form of a relationship between physical quantities when the mathematics is too difficult. Ordinarily, mathematics is a bit difficult, but we are looking at, you have a relationship and the mathematics involved is a difficult one. Through the help of dimensional analysis, one can easily get the relationship. Let's look at an example to see how we apply this. Example. Let me read out the question, then we can see how we'll go about it. Okay, this is the question. A small mass is suspended from a long thread so as to form a simple pendulum. The period of oscillation depends on the mass, the length of the thread, and the acceleration of free fall at the place concerned. Given that T equal to K mx L y g z, where x, y, z are unknown, and k is equal to 2 pi. First question here says we should find the value of x, y, and z. And the second question says hence derive an expression relating T, M, L, and G. So we have a question before us. This is the mathematics. Looking at it, you know it's really too difficult to go about it. So we have to find a relationship between T, M, L, and G. So the equation, something like this. You have a pendulum bob the mass, m, the length of the thread, then the period of oscillation as you display it, and the acceleration due to gravity. So we are to find a relationship using this, relating the period, the mass of the bulb, the length of the thread, and the acceleration due to gravity. So it's a complex relationship, but through dimensional analysis, one will be able to find it. So let's look at it. How do we go about that? So the first thing, this is the expression that was given, T kmx ly g z. So we are to express it dimensionally. K is already a constant, the value is given. M is the mass, and dimensionally, how do we write mass? Capital M. L is length. G is acceleration due to gravity. Dimensionally, we have written that before. Acceleration is velocity, the rate of change of velocity over time. So dimensionally is what? L t to power 2. So we can write L t power 2, this z. We have not done anything. We have just moved from here to this point, expressing it in terms of dimensional analysis. So the next thing, open the bracket. This will be L z t minus 2z. The next thing, k mx, we have L to power y, L to power z. Using law of indices, multiplication, you add the two power together. So the next thing we'll do is that looking at the left-hand side, there is no mass, but we can introduce mass to power 0. There is no length, we can introduce to power 0. From law of indices, anything raised to power 0 is 1, and 1 times will give us the same value. And anything raised to power 1, this is raised to power 1, but it's not visible. Anything raised to power 1 is that value. So what we'll do now is to compare left-hand side and right-hand side. M here, the power is 0. We are looking at it in terms of the power. M here is 0. Are we together? So let's call this 1. The next one, L. L here, the power is 0. And the power here is y plus z. Let's call this equation 2. T here, on the left-hand side, is 1. And is equal to what? Minus 2z. Call this equation 3. So from equation 3, z is equal to minus 1 over 2. If we substitute here into equation 2, so from equation 2, we can have that y equal to half if we substitute for z. So from here, we have gotten the value of x, value of z, and value of y. So the first question here says we should find the value of x, y, and z, which we have gotten. Okay, the next question says, hence derive an expression relating t, m, l, and g. How do we do that? This is the equation given, kmx ly g to power z. All we need to do now is to substitute for x, y, and z. So the value for x is 0. So you have k m to power 0, l, y is half, g is minus half. Anything raised to power 0 is 1 when you multiply. Then k is 2 pi. So let's substitute for k, 2 pi. This one is 1. When you multiply, you have L half G minus 1. So this will give us 2 pi square root of L over G. So from this complex expression that we were given, we were able to find the relationship between the period of oscillation, the length of the thread, and acceleration due to gravity. I believe we are familiar with this expression. So this is another application of dimensional analysis. We use it to do what? To derive the exact form of a relationship between physical quantity. These are physical quantity. Length, period, time, they are what? Physical quantity, even acceleration due to gravity. So we use it to derive the expression when the mathematics is too difficult. As we have seen here, the mathematics is a bit difficult. But through dimensional analysis, we are able to what? Get the expression. Okay, let's look at another example of how we can use this. Example 2. I will read out the equation, then we can look at it and solve it like we just did for this very one. So I hope this is not difficult. It's very simple if only you understand. Okay, we have another question. A wave is set up in a stretch string. By plugging it, the velocity of the wave depends on the tension in the string, its length, and its mass. Given that V equal to K Tx L to power Y M to power Z, where X, Y, Z are unknown and K equal to 1. The first question here says we should find the value of X, Y, and Z. And the second one say hence derive an expression for V, T, L, and M. So if you look at it very well, this is similar to the last one that we just solved. So let's look at it together. Solution. We are given V equal to K Tx L to power Y M to power Z. So what is the first step? You look at the physical quantity, then you express it dimensionally. V is the velocity. So dimensionally, velocity is expressed as this. You remember. Then this is a constant. T is tension, and tension is the same as force. So how do we write force dimensionally? Force is mass times acceleration. So LT to power 2, and it's raised to S here. Can you see that? Then L to power Y, M is the mass, and it's raised to power Z. So the next thing here, you open this bracket, and if you do that, we'll have K, M to power X, L to power X, and T to power minus 2X, Ly, Mz. So applying laws of indices, k is a constant. We have m here, we also have m here. So if you have the same base, you add the power together. So taking x, m to power x plus z, L is here, L is also here. The same base, add the power. Are you confused? No. So we have LT to power 1. So what is the next step? Who will tell us? Okay, the next step is that we have L here, we have T here. We equally have on this side, we have M here, but we don't have M here. So we introduce the mass to power 0. Remember, anything raised to power 0 is 1. When you multiply, it stays the same. So the next thing, you bring out equate the power, the left-hand side to the right-hand side. The first one, let's look at the mass. The power here is 0, and 0 is equal to what? X plus z. Let's call this equation 1. Which one is the next one? L. The power of L here is 1. 1 is equal to what? X plus y. Let's call this equation 2. Then the next one, T. The power here is minus 1. The power here is what? Minus 2x. So minus, okay. So from here, x will be equal to what? Minus 1 over 2. Are you following? Okay. From here, we have known the value of x. If we substitute into y, we will have okay, let's look at it. Okay, let's look at it. Sorry. Y is here. T is minus 1, minus 2 here. So minus, we cancel minus. So x will be half. Sorry for that. Then we have known x to be half. From here, y will be equal to, substituting this into this place, y will be equal to half as well. And z, substituting here, z will be equal to minus 1 over 2. So the first question says we should what? Find the value of x, y, and z. So the value for x is half, value for y is half, and the value for z is minus half. Okay, we have gotten the first part. The second part says we should find an expression that is relating v, t, l, and m. So from here, all we need to do is to substitute for x, y, and z. So x is what? Half. So we have t to power half. L is, y is also half. And m is minus half. So from here, we can write k to be this v. So this is an expression that we use relating the velocity of a stretched spring to the tension in the string, the length of the string, and the mass. The k here is the spring constant. Mind you, for this very equation, the value for k is 1. So when you substitute, you have this expression. So this is the expression we are looking for. And we use this this give us relationship between velocity of a stretched spring, a vibrating string, to the tension, the force applied, the length of the string, and the mass. So through the use of dimensional analysis, like we say, we use it to derive the exact form of relationship between physical quantity when the mathematics is too difficult. So through dimensional analysis, we have gotten the relationship between the velocity of a vibrating stretched string to the tension, the length, and the mass of the string. The K is the spring constant. Thank you very much for watching. Please like, share, and subscribe to my channel. Watch my next video on scalar and vector quantity. How much do you know about scalar quantity? How much do you know about vector quantity? In the video, we shall look at addition of vector, subtraction. Shall also look at resultant vector, resolution of vector, and other things. So please watch my next video on scalar and vector quantity.